in the internet run in both together run in an overloaded router. And just having some different ends TCP flows coming that both have an overlapping route. They hit a router that is overloaded. If that router is overloaded, TCP will give them about equal throughput. So it has some fairness properties. We don't see the fairness properties that are resulting from this local behavior. What we will only study is the single behavior of a flow. In the lab, do you do fairness in the lab? Is that right? Measure? Do you do it? Very difficult to do, if you're having only a small number of flows. But this is the global effect. That is the part that has to be studied, and it involves the solution of differential equations. But there is really something that emerges as a global property. So the TCP algorithms have globally very desirable properties. If you're running, this is the thing. You're running into a network, and right now you're not concerned about being shut out. What happens is if your traffic and somebody else's traffic hits a bottleneck, you get about the equal throughput, the same throughput. So, which means that resources on the internet are somewhat, if they're using TCP, resources are somewhat proportionally allocated, equally allocated. UDP would not do that. UDP kicks everybody out. And that's why UDP traffic is not very desirable. And that is also why there are, I mentioned this when I gave an overview of transfer protocols, that there are enhancements, new protocols developed in the last 10 years that try to enhance UDP by adding congestion control algorithms. And that's the objective, to add this global behavior of fair throughput if you're hitting the bottleneck. All right, so let's get going on congestion control. All right, so the mechanism for congestion control is a mechanism by which the sender reduces its transmission rate if the network is overloaded. It's a voluntary action. This is done in TCP. This is done by setting a window, the size of a window. We have seen in flow control that there is a flow control window. This is the size of the advertised window. This is something that the receiver tells the sender, data coming from the receiver. That is used for flow control. That is the flow control window. There is an additional window, the congestion window. The congestion window is determined by a computation that takes place exclusively at the sender. And what you have to think about is both of these run at the same time. Flow control, congestion control runs at the same time, setting these windows. What you can actually see, what the sender can actually transmit, the number of data that it can transmit, is then the smaller one of the two. So, flow control window is advertised by the receiver using the, we've seen this. Yeah, this was here, the window size, which is sent as part of the acknowledgement. The congestion control is adjusted based on feedback from the network. It's adjusted at the center. So the basic congestion control algorithm, what I discuss here is the core basic congestion control algorithm. It is done with the help of two variables. There is the congestion window. The congestion window is the size of the congestion window. CWDN stands for congestion window. That is this part here. Then there is something called the slow star threshold value. That is the second variable. I want to tell you how it's being used for the so these are the two variables. Now, the sender, with regard to congestion control, the TCP sender is in one or two modes. It's either in the slow start phase or it is in the congestion avoidance phase. You have to cut me some slack here. I need to use this terminology. Yeah, slow start phase, congestion avoidance phase, and the phase that it's in is determined by these two values. So if the congestion window is less than the slow start threshold, the sender is set to be in the slow start phase, and if the congestion window is at least as large as the slow start threshold in the congestion avoidance phase. So this is the TCP congestion control algorithm. Initially, connection starts up, nothing has been sent. The congestion window is set to 1, and the slow start threshold, the initial value, is the advertised window. This is the window that from flow control that the receiver, the other side, sent to the side. So this is the field that is sent this is coming from the window flow control information, which is passed back and forth initially, even during the SYN packets. They contain the window size information. So now what's happening is that the congestion window is the maximum number of bytes or packets, but TCP keeps track of bytes. For convenience, we'll just sometimes we'll count packets. The congestion window is the maximum number of packets that can be sent. This is kind of a second constraint on the window. So what's now happening is that the sender will increase its congestion window. Initially, this one here is counting here packets. Initially, the sender can send one packet only. Then it has to wait for an acknowledgement. So it has to start very slow. That's where the slow start comes from. All right, so initially set to 1. No matter what the advertised window size says. If the advertised window says you can send, and you see it, 16,000 bytes, initially you can only send one packet. Yeah? And what's the size of the number of bytes then? This is always then multiplied by the maximum segment size. That's the number of bytes. Okay, so now, when an acknowledgement is received, and the sender is in the slow start phase, it increases the congestion window by 1. I send the packet, I cannot send anymore, I get an acknowledgement back, then I increase the congestion window by 1, so it's now 2. Then I can send 2 packets. Assuming both are being acknowledged, each acknowledgement triggers an increase of 1. So in this way, you see here the congestion window is increased. Now, at one point, the congestion window has reached the threshold value. If it is larger than if the congestion window has reached the threshold value as stressed, then it's in the congestion avoidance phase, and then it increments the congestion window by 1 divided by the congestion window. What this means is that the congestion window is increased by 1 if it has received CWND many acknowledgements, roughly. So this is just this is an increase, this is in the congestion avoidance phase, the increment is just much slower. So you're first increasing fast, then you're increasing slowly. That's the idea, the congestion window. And then the congestion window grows and grows and grows. What's the maximum size of the window? Well, it's 65,000, 2 to the 16, the same window size as the window, the advertised window. Now, So this is only the increment of the congestion window. How is it decremented? Well, whenever there is a timeout, and the timeout is the retransmission timeout. Whenever the retransmission timeout kicks in, the slow start threshold value is set to 1/2 the current congestion window size, and the congestion window is set to 1. So that's something very similar to the size of the congestion window after a timeout is really set back to the same value that exists when the connection is open. Any questions on this? Yes.
Why doesn't the algorithm just stop somewhere?
It stops at 65,000.
Okay. But as soon as there's a timeout, it just goes back to 1.
It goes back to 1.
Okay. My question was, is that very wide?
This is a deep question. This is what has been studied. Locally, it appears to be very unwise. At the global level, replacing it with something that is wiser. This is from 1988, by the way. Yeah, so this is about 1988. There is, let's see, there's no short answer to this. Yeah. Roughly, this algorithm is like this. Actually, Linux is using a somewhat different version, but it's using Linux recently introduced a different version of congestion control, and I question if that's a good idea. This is the main algorithm that is still being used by most systems. And it's called Windows Max algorithm. It has not been replaced. There is a behavior here. You see this is an increased behavior and a decreased behavior. This particular behavior is it's called additive increase, multiplicative decrease. If you're adding by a constant, and there are two different, let's see, here pretty much you're adding by a constant. And you will see that window grows linearly. Here you're decrementing proportionally, and the important value here is cutting by half. You're kind of cutting back the behavior proportional to the current value, multiplicative decrease. Now, I could add a lecture on that, on why this additive increase, multiplicative decrease, results in fairness if I have two connections running against each other. And there you will see it's a good choice, opposed to other algorithms. Setting it back to 1 is bad, because you're essentially shutting down your connection. Every time retransmission happens, the TCP senders will say, "Oh, the network is congested. I should only send 1 packet and wait for an acknowledgement." That's just very strange. It's very, very careful behavior. So what happens is there have been, and I will talk about that. There have been modifications made to this basic algorithm that try to avoid this in less severe situations. If you're having a hunch that something not so bad, something bad has happened but not so bad, like a packet has been reordered. If the sender can get a clue of that, it only has to guess, it never knows. If the sender gets some indication that possibly a single packet has been lost, that you can have an optimized output. But for an timeout value, it still goes down to 0. And what it sees is just overall, just to give you the behavior of a connection. If you're taking, this is the congestion window of TCP over time on a congested link. This is a typical scenario that you see. What you see is, you see it here, slow start phase, a very steep increment, then a slower increase, that's the congestion avoidance. Then here we are at 60,000, yeah? The congestion window is then dropped from 60,000 back to kind of one segment, like 1500 bytes. But you see here that by the slow start threshold value, it goes very quickly back to this value here, which is half the original window size. Yeah, so that's pretty much what that's why I said this piece is really the important part. Because here you're within a few round trips, because you double each time with acknowledgement, you're recovering the slow start threshold value very, very quickly, but then you're moving slowly. Yeah? So if you're having consecutive losses, you see it here, I climb, get to this value, then I cut down, get to half pretty quickly, go here, then I have another loss. You see that the more losses you occur, the more conservative, the slow time. This is clearly here a sequence of multiple losses. You are kind of setting the congestion window to a small value. Here is a period of very few losses. Well, you know, this is what you're paying for. That's the cost of this output.
How can it go up so fast if it's incrementing by one?
Yes.
Not multiplying.
Okay, so I skipped a few slides and I'll go back to this one.
Oh.
All right. So this is the algorithm, and I'll go discuss it now. Yeah, so the initial value is, this is just some more details. Initial value congestion window is equal to 1. You know, in TCP, the bookkeeping is done based on bytes. So when I say 1, it's like 1 segment. Yeah, 1 multiplied by the maximum segment size. Each type of ACK is received by the sender congestion window is increased by 1 segment in the slow start value. If an ACK acknowledges 2 segments, the congestion window is still increased by 1. If an acknowledgement is received for something that has been previously acknowledged, not incremental. So that's why it says kind of a new ACK, or ACK for new data. Even if an ACK acknowledges a segment that is smaller than MSS bytes, it's incremented by 1. And so this is just kind of more details, yeah. So it's essentially a counting of 1. In general, a TCP receiver sends an ACK for every other segment. We know it by, if you're sending a lot of data, because of delayed ACK, we expect that we're getting an ACK for every second segment. I'll take this. This is where everything gets coupled. Yeah. So what I'm going to do is I assume now that TCP segments are sent, that acknowledgements are sent for each segment. And you can know this for a while, because otherwise we'll just have too many algorithms in our head. It does not change the overall behavior. It dampens a little bit, but it does not change the quality of it. So the question is, that was your question, yeah? Does slow start increment slowly? In fact, not. It increases exponentially, and this is how it goes, yeah? So suppose this is the sender, this is the receiver. We start with a congestion window of 1. We send a segment, we get an ACK. Then we send the congestion window equal to 2. Then we send 2 segments. Each of these gets acknowledged. I set the value to 4. 4, 8, so this goes. In each round trip, I double the size of the congestion window. So, yes, it is called slow start. You have to get over that. Yeah. So the first, what slow start expresses is that you initially start at a very small value to be as conservative as possible. But then you're ramping up relatively quickly. So you can see that this period here is only a few round trips. Yeah? And you see it in this behavior here, that kind of this fast increment here, yeah? Here you see it, yeah? So this is the slow start phase. see it here in this big window directly. Yeah, so you can, you know, you really can see the doubling here. Yeah? This is from a simulation, but it's a decent simulation. All right, so that's what we've seen. So then it comes to the congestion avoidance phase. The congestion avoidance phase is, you know, you just increment by a fraction of the congestion window. There is a debate whether this is the, you know, whether you should take a snapshot of this. Just read it as it is, that you have to get this many acknowledgements before you increase by 1. So the congestion window is increased by 1 only if all congestion window segments have been acknowledged. So now we can put these things together and see what's going on. So let's suppose we're having a TCP sender with a slow start threshold value set to 8. So then it goes. 1 packet, initially congestion window is 1. I get an F, and it's sent to 2, send 2 packets, get 2X, send 4 packets, 4X, 8. At this point here, you're entering the congestion avoidance phase. You send 8 packets, 8 cycles, all of them acknowledged. Then you go to 9. Yeah, so this is now you're increasing by each packet results in an increase of 1/8. So you're getting 8 of those. You increase. Here you're getting 9 packets. So it's a very slow increase. And so if I do here, if I count the round trip times, round trip time is kind of the time to send my entire window and to get acknowledgements back. If I count that as a round, let's not say round trip time, rounds, number of rounds. Then in the first round, my congestion window is 1, and the second round is 2, 4, 8. Yeah, and then it goes linearly. So, and this part here refers to an additive increase. We're increasing the window at a constant rate. And the rate that it increments is pretty much the rate at which a full congestion window has been acknowledged. Yeah.
So, is it like a double float value? You can have decimal places because you're adding 1/8, for example. And then once you update it, isn't it going to be 8 plus 1/8, and then you take advantage of that? So it's going to be above 9.
Yes.
Or do you keep track of have I gotten 8 packets back to 8 acknowledgements?
Well, the thing is here that, yes, so this is all in the code, yeah, that implements this. The counting is based on bytes. So with bytes, then it really does not make a big difference. And so if you're reading the code itself, it's actually more like this. You see it. While exactly, what you should say is, you know, take the old congestion window. So what this pretty much says, increment by 1. Remember the congestion window. Count the number of acknowledgements coming in. If you get C, W, and D acknowledgements, increment by 1. And that's not, if you look reading the Ben Jacobson, which actually, you know, tried to go to the bottom, but you have to read the code of this is the previous kernel implementation, and it's actually done more in this way. But I don't write bytes here because it gets all confusing. The algorithm is, this is the algorithm. And you see what's going on. Yes.
So if the sender sends 2 packets, and the receiver has some delay, and then sends 1 acknowledgement that acknowledges both,
yes. No, it would only increment by 1. So what you see then is that, you see, but you know, if you're acknowledging only every second packet, this one here is kind of just reduced by 1 round. You get half as many acknowledgements, which means everything. So you're getting for 2 you're getting 1 acknowledgement. For 4, you're getting 2. For 8, you're getting 4. So you're just 1 round trip behind. It doesn't have a big impact. Yeah. Yeah, but if I present all of that, then you can't figure it out. Yeah. So I just did not show the delayed acknowledgement. But you see, it doesn't have a big impact. So that's a slow start. Yeah? So pretty much. So now, how does? So this is the increase of the congestion now. How do you go down? So this is the rule. TCP assumes there is congestion if it detects the packet loss. The packet loss is detected. It says it is lost because of congestion, not because there's interference or what else could happen. Random errors, bit errors, transmission error, what could happen. The TCP can detect lost packets in 2 ways. The TCP sender detects packets in 2 ways. There's a timeout, the RTO timer kicks out. The second one, you're getting duplicate acknowledgements. Because if you're getting an acknowledgement, it acts only in increasing numbers. So if I send a packet number 2, sequence number 2000, I get ACK for 2000, 3000, does not arrive. Then I send 4000, I get still 2000 back as acknowledgement. I send 5,000, still get 2,000 back because packet 3,000 has been arrived. So if you're receiving multiple duplicate if you're receiving duplicate acknowledgement, something went wrong. Could be out of order delivery, could be a loss. So that's what a TCP reacts to. So whenever, so this is the standard procedure is a timeout is a binary congestion. Binary means on and off. It doesn't tell you a little bit congestion. It says there's no congestion, increase, or it says congestion, shut down. That's the signal that is being interpreted. When a timer occurs, the sender performs, does this congestion window to 1 and half sets the slow start threshold value to half. Yeah, and then it enters slow start again. So this is then this behavior where you see pretty much what is the slow start threshold value cutting this in half. It means, you can recover half your window very quickly, but then, because at here something goes wrong, so slowly go back and more carefully increase starting at half the value. Yes?
At the start of a connection, is it the sender that advertises the window, or is there a signal?
So congestion window is not advertised. At the start of the sliding window, the flow control window is advertised. Let's go back. There are 2 windows. There's the flow control window and there's the congestion control window. The congestion control window is only done by the sender. If you have client and server, both sides are sending. Now when I say sender, I'm the client, there's the server. I'm talking about the sender. The client is sending, the client then has a congestion window. And it receives the flow control window from the server. From the server's perspective, the server is also sending to the client. The server gets its flow control window from the client. And the congestion control window, the congestion window is set by the algorithms running at the server. Yeah, so both client and server can act as sender. When I say sender now, it's either side of the connection. Flow control is set by the receiver. The receiver talks to the sender to reduce the rate or increase the rate. Yeah, being rate size of the window corresponds to transmission rate. Congestion control, the sender listens to what's going on in the network to reduce its rate. What you can really send is the minimum of the 2. This here should be set to the value that the network can tolerate. This should be the value that the receiver can tolerate. The smaller one is what I should send. Independent action. Receiver can be doing very fine, but the network is congested, or receiver, the network is not congested at all, you can send as much as you want, but the receiver is in dire straits, both times you have to do this. These are independent mechanisms, they're completely orthogonal. Alright, so these are now the flavors of TCP congestion control. So what I don't like about it is that recently there have been, congestion control algorithms in Linux have been modified. They don't obey it. And what they do is they do something that is somewhat more aggressive. It's called the big algorithm, binary increase congestion control. And then they figured out that doesn't work so well, and it was then changed to something called cubic. Well, I don't want to go into it so much. Yes. Let's see. So this is the basic algorithm. They have names. There's Tahoe, Reno, New Reno. People know this, but they're doing networking. TCP Tahoe. TCP Tahoe is the original congestion control algorithm. It has slow start, it has congestion avoidance, and it has something called fast transmit. Then there's TCP Reno. It then has something added which is called fast recovery. We'll discuss that. And there have been further refinement called New Reno. I don't even, it gets so subtle at these points that going over it at this level does not quite help. And then there are other pieces of congestion control that happen, like selective acknowledgement. Then you would think that this is an error control algorithm. No, it is actually in TCP. Selective acknowledgements have been added to help with congestion control. And all of what these algorithms do is they try to avoid this behavior. They try to somehow kind of cut into half, but not try to avoid slow start. Slow start behavior. Very difficult to work with this, change this formula. Let's see. Then there's something. Yeah, that's not good. Random early detection. Also something that existed for almost 20 years. Is it all routers? Nobody knows how to configure it. So the idea here is that the router does not wait if the router is congested, it drops packets. Congested means the buffers fill up, which causes them retransmission time. The idea is, well, isn't it better if you're not waiting until you're really full, but if your buffers are filling up, that you start to selectively drop packets, causing some selective timeout values. So therefore, not have these emergencies, but you somehow force these senders to slowly back up when congestion develops, not when it has happened. It's something like on the Gardener, if it tells you slow traffic, downtown area, then some people may decide to get off. But at the same time, if you see that sign, you're stuck in traffic, and there's no exit, and that's kind of the scenario that one is running into. If congestion is very difficult to avoid in a decentralized scheme, and you don't. The most difficult part of networking, building a large network, more difficult routing, large-scale routing, and congestion control. The most difficult pieces of networking. Anyways, okay. So what I want to discuss is how fast retransmit works and how fast recovery works. Let's just look at the acknowledgements of TCP. So we have, this is something that we saw earlier, that we saw on Tuesday. We're sending a 1 kilobyte segment, we get an acknowledgement back, so 1024. Then we're sending another packet. We're getting at 2048 because we sent 2000 packets. Then we send the third packet. That third packet doesn't get there. Then we still can send, yeah, we have another packet. We send with signature 3072. Then our getting still act number 2048, because the acknowledgement is always acknowledging the largest kind of 1 plus, whatever you have received, plus 1. So it's sending 2048. Because that's what it's expected. Cannot send anything else. So this is a lost segment, so what you can say is, well, if you're getting 2 packets, 2 acknowledgements that are identical, well, then you know a packet has been lost. That you know, but you also know that something gets through. So the network is not really congested, just something went wrong. You see what I'm saying? This acknowledgement comes back, and it acknowledges something. So something that I send gets through. So it's not that the network is congested, just something went wrong. Now, if you're getting 2 acknowledgements here, something can happen like this. Well, it could also be out of order delivery. It could be that the packet just was delayed a little bit for whatever reason. Yeah, went into the slow path of the router, something could happen. Then the third packet arrived earlier, triggered this acknowledgement. So here, both the so nothing goes here, nothing goes bad. At this point here, you would then send, well, to acknowledge here 3072. Plus 1000, so 4096. Yeah, what if you send at this point? But if at this point here the receiver then says, well, this is a lost packet, then if it starts to retransmit it, you will have a lot of unnecessary retransmission because you cannot tell the difference from here to here. That's a little bit, yeah, the tricky part. However, if you get multiple, if you're now sending multiple packets and you're getting multiple of these back, then there's increasing evidence that this packet has been lost. And that is what TCP has implemented. So you have the situation, having the packet, second packet gets lost. Then you're sending the third packet, triggers the same acknowledgement. Yeah, 1, 2. Then you send the fourth packet, still the same acknowledgement. The fifth packet, the same acknowledgement. So at this point here, TCP is implemented to say, I get the third duplicate acknowledgement. I bet this packet here has been lost, and then it does something. It just, out of the blue, just transmits this single packet that it believes to be lost. So this packet here that is following the acknowledgement, yeah, this is here the sequence number from 2024 until 2047. This packet is just being retransmitted. Just, it's just happening. If it can send other packets, it just continue normal behavior. Just interjects this one. That is called fast retransmit. It's just a gamble that is saying, and why 3? Why not 2? Why not 1? Well, because 1 is too few and 5 is too many. Yeah, people pick the number. That is what they pick. Yes.
What about the other acknowledgements for the other packets that get sent through?
Well, at this point here, the whole sequence is being sent. At this point here, if this one arrives, the acknowledgement here will be 6,144.
What if something else was lost in between, though?
Then retransmit can only deal with a single lost packet. If it has multiple losses, it doesn't do that. This is where this other optimization, new Reno, comes. So the second, it means fast retransmit helps in some situations with single losses, but you can only have a single loss in one round trip. you have multiple losses in one round trip, then all bets are off. You're falling back to RTO. Yeah, it's nothing is happening. You still have, you're waiting for. Your retransmission timeout is still set, so eventually you will time out and then retransmit. The retransmission will happen, but you're then having a timeout. Because of the timeout, you go back to slow start. All right. So the original fast retransmit actually it did this optimization, but then went back to slow start. This is then when this kind of an improvement was made, which is the intuition is here that this is something that you're getting into this third duplicate act in the situation. You're trying to avoid entering the slow start phase. In fast recovery, what is happening after the fast retransmit, it's entering the congestion avoidance phase. So what you're trying to do is this. This is after fast retransmit. So this is here the version here, fast retransmit or fast retransmit, but no fast recovery. You have a slow start, congestion avoidance. Then you have this out of order. Let's assume you're having a single packet loss. Fast retransmit, I enter the slow start phase. So this is my situation. What fast recovery is trying to do, it's entering the slow start phase, the congestion avoidance phase, but then it kind of goes back to this point, which is the slow start half. It starts at the slow start threshold value. Well, it starts at half the congestion window and enters congestion avoidance directly. So it cuts out the slow start phase. Do you see this, what's going on here? Now, how is this done? Yeah, so this is done when I go back and say, well, So, what it does, if you're getting the third duplicate act, third duplicate acknowledgement, that means you're getting the fourth acknowledgement for the same data. That is identical. Yeah, this is the original acknowledgement, then I have first duplicate, second duplicate, third. At that time, you're setting the slow start threshold value to half the congestion window, and then you retransmit the packet, and then when an acknowledgement arrives that acknowledges new data, meaning acknowledgement that you have that is not a duplicate of what has been earlier acknowledged. Then you're setting the congestion window to the slow start threshold value. And that's the thing. Yeah? So what you're essentially doing here is, if this is happening, you're retransmitting. You have set the slow start threshold value to half the congestion window, and then you set the congestion window to the slow start threshold to enter in this phase. Now, there are a couple of pieces in here where the slow start threshold value set to congestion window half, then it increases the congestion window by 3. Why does it do it? It does it to account for the packets that have been acknowledged for these. It's pretty much the X. If it is in a slow start phase, and each of these duplicates has triggered the addition of 1. Yes.
So if after sending the sequence number 1024 again, and we still get 1024 back acknowledgement, do we go back to slow start?
Let's see.
We receive the
Yes, so which means that this packet is not arrived, yeah?
Yeah.
So you're getting this back.
So there's probably a connection probably, right? Or something. Or
Yeah, I mean, there is more than, there are multiple errors. There are multiple losses, yeah? In this case, this no longer this doesn't do anything anymore. Yeah.
So it goes back to the start.
It then just continues. So it will the sender will continue sending until timeout happens. If the timeout happens, it will then end. So once the timeout happens, it then enters the slow start phase. Yeah. So if this was a timeout value, it would still go into the slow start phase. Timeout still called slow start. And what you're trying to do is you're trying to optimize it. Well, I think I'm over. Sorry, I hate to run over. Sorry, I didn't notice that. I may look back at this on Monday, just review it. There are a lot of details that have to get used to. This kind of give and take on how much detail I give and how much I withhold. This is what actually I think you can do it.